Okay, so once again you are most welcome. We are back in style. We are back in style. Now this time round you are going to be in for Umta Moko Examinations Board. Okay. Okay, so without wasting time, I think we are in for our Umta. Okay, yeah, I've been receiving very many texts over the guides concerning Umta, and please, here we got you covered. All right, now we are going to look at the now please maybe just make some clarifications please. You when you look okay, here on the channel, first of all we deal with all level content. Reason, the new curriculum L level is a bit having a lot of questions actually, so and I don't want to upload something which will be debatable later on. So for now we are still keeping on to the all level content, and if it so happens that the new curriculum is well streamlined, meaning the setting formats and so on, we shall step in for it without wasting time. Once again, my name is Mtanda Samir. Please, for anything, you can hit my inbox just right at the bottom of the screen there. Okay, now we are going to look at the Umta Physics 2025. Okay, good. Hope you enjoy the video, and without wasting time, let's get there. Okay, great. So once again, we remind you to subscribe to the channel. Please, I said that somewhere in okay, we are going to have this channel limited to only people who have subscribed to it. So before you complete this video, if you have not subscribed yet, better stop, pause it, you go and subscribe, because soon or later we shall be monetizing or making this channel okay limited to only our subscribers, and whoever will have not subscribed will first of all have to pay some money to watch the videos here. But think about it. I kept telling you this, that why to pay, yet just a simple click onto the subscription button gets you there. Free cost, free everything. So I beg you, let's get that done such that we don't miss out. Anyway, let's get there to the question. Okay, good. Now we have our UCE Umta 2025 physics as requested by some learners who are also my friends. Okay, now here let's get our laser pen. We look into this now. Please, if you don't have enough time to watch this video, I just request you pause it and you come back for it that time when you're really free, because it has got a lot to learn, by the way. Yes, and I know by the end of it all you'll be able to learn something if you're a student and if you're a teacher as well. All right, good. Let's step in for it. The same during UPDF pass out ceremony. Anyway, the army band performed using different instruments. While the audience enjoyed the performance, many struggled to distinguish the different sounds produced. Later, one of the recruits collapsed from the fatigue, and was rushed to the hospital. Dr. Kirabo, the army doctor, examined the patient, but had difficulty in reading the patient's previous medical records. She suspected that the power of the spectacle lenses, take note of that word, lenses, might have weakened. She recommended that a laser-based endoscopic it was meant to be endoscopy for a more detailed internal examination. Due to her busy schedule, Dr. Kirabo asked her assistant to help verify her lenses. Again, the word lens is coming back. The assistant placed medical records 20 centimeters in front of the lens and observed that the image was formed 60 centimeters on the opposite side of the lenses. Good. They needed to determine whether the power of the lens was still in the acceptable range of 5.0 diopter. Now, this diopter, the unit for measurement of power of a lens, to 6.0 diopter. Alright, good. Now, maybe the SP is like this for someone who may not be knowing. The SP of that diopter in full is like this. and that's how I pronounce it. I don't know how you really pronounce it, but this is how I pronounce that statement there, diopter. That's how I pronounce it, D-I-O-P-T and E-R. Okay, good. So let's proceed. Now, okay, we have some pictures here. I think this is the recruit who has collapsed. Okay, the recruit is here who has collapsed. Now this is what we call an endoscope. They enter, it's more like a tube which they enter into your mouth. Just imagine, okay, well, an imagination, just imagine they just get a pipe, a plastic pipe, then they enter it into your mouth and it goes up to your stomach. That's how an endoscope works. I know what you're feeling like. You can't bear with the session, but of course this is a medical procedure which is required in some cases. Okay, good. Now, task is the same. As a physics student, part A, help the assistant in determining if the lenses are still suitable for use. Now, of course, if it's a lens, you must check about its power. Good. Decide whether the laser light in figure 2 will be trapped and transmitted through the pipe. Will be trapped and transmitted through the pipe to the other end. Explain your answer. So they're like, will this light ray, this laser here, be transmitted through the other side? Shall be looking into that. Explain why laser light is preferred over ordinary light. Shall be looking into that. Part D, the last one, the same. Explain how understanding pitch, loudness, and quantity, is it quality, which they call timbre, helps distinguish between different musical instruments. Okay, we shall be stepping in for that. Now, without wasting time, let's, I think, look into this part A. They're saying, help the assistant in determining if the lenses are still suitable for use. Now, are the lenses still suitable for use? Somewhere here they've given us the recommendation. Like they've said, at this level, this one here, this is the, if the lens can have a power of this kind here, then in that range actually from 5 to 6 diopter, then that lens can be considered to be good. It is between 5.0 to 6.0 diopter. Now guess, if it is less than that, then it will be of less power, not good. And if it is more than that, it will be very strong, also not required. So it must be between 5.0 and 6.0. And now, what does it mean? We need to go in for that. But what must you know first of all? You must know that power of a lens is equal to 1 over, the formula is equal to 1 over the focal length. But remember that this focal length must always be in meters. Now ask yourself, what do you want? Now we want power, but do we have the focal length? Yes, by the way, we need the focal length. How shall we get the focal length? Like we are. Look at it, they're saying that the assistant placed medical records at 20 centimeters. Now this one here will be medical records at 20 centimeters in front of the lens, meaning, let me just give you a sketch. Here we are, and this is our convex lens. Just want to give you an imagination here. Okay, good. Now the medical records, maybe they are here, placed at that level, and the distance from there up to here is 20 centimeters. Now what I think about, that's object distance, 20 centimeters. So that's object distance. Then they said, and they observed that the image was formed 60 centimeters on the opposite side. So the image was formed somewhere this side, maybe. This is our image, say I, and it's formed 60 centimeters away. Okay, 60 centimeters away. I think that now this is our U, object distance, and this is our V, image distance. Now what do we need? We need the F, which we shall use to calculate the power. Which power we shall compare with this and see how our answer will be. Now, when we look at this, I know what you're thinking about. Now I know you're thinking about this. The 1 over F equals to 1 over U plus 1 over V. But please, if you try to check very well, this formula here is only acceptable for mirrors, curved mirrors, but with lenses, you know, it is beyond, it's not in the syllabus. Like, meaning, this lens formula is not allowed to be used in all level. It is not allowed to be used in all level. So, and when we are dealing with lenses, so we cannot use calculation as a method to get it focal length. We shall not use calculation, but remember there are two methods. We have by calculation or by graphical method. So here for us what we're going to do, we are going to use graphical method. I've explained why graphic is because the lens formula is not acceptable right here. Okay, hope that makes that bit of sense. Now let's go in for that. We go and get that answered straight away. Okay, now without wasting time, let's go and see how part A can be answered. Let's go there. Now first of all, we shall need our graph. Like, do you have it right there? Now from the question, You all remember that we had that object distance was 20 centimeters and the image distance was 60 centimeters. Now a question comes. Do you have the object height? No, we don't have it because they gave us only. We don't have the object height and image height. What I'm meaning is this. Fine, we shall be able, like, we are going to use graphical, which means that we're going to do this and we shall have our lens right here. Now we know that. Now we don't want to know how long shall we draw our object, like meaning the height, because we know the distance is 20. And how shall we do our image? Because I know the distance here is 60. But how the height of these ones here? Do we have them? Not really. So what you're going to do simply, we are going to also find a way of getting the height. But you all know that the magnification can get us there. Like say for example, we shall calculate the magnification. You all know that we have this formula here, m over v is equal to the image height over object height. We can use that approach. However, for me, I'm going to first of all consider m over u, the formula for magnification. Then later on you shall have to relate. Now we start. We say, now for magnification, the formula is given by m over, the other m is equal to v over u. Now we substitute in. Remember our v was a 60 and our u was a 20. So there, our magnification will be equal to 3. Now, what do we mean by magnification? Like, when you say magnification is equal to 3, what does it mean? We have it here in the statement form. We say magnification is a 3. Okay? This means an object of height 2 centimeter forms an image of 6 centimeter long. I don't know if I can really see that. A magnification means that whatever we do in the object, we must multiply. So if the object, we are going to relate that. If the, for us, we are saying that with the construction you're going to use a height of 2 centimeters. But a height of 2 centimeters, this magnification means times magnification. So a 2 times 3 gives you a 6 centimeter long of the, of the image. And that's what you're going to do. Now, in this context, what you must know is that they've given us the image position. And we have the object position. So our aim is to find focal length, but using graphical method. How do we go about that? Now still here, we shall start off by getting our principal axis, which you have right there. That's our lens, our convex lens. Then we're going to draw our principal axis right there. That's our pole. We're going to draw our principal axis right there. Okay, look how cool that is. Now, having done that, what you must know is that, now like I'll give you a rough sketch. Like our object is going to be of height 2 centimeters. But the object is at which position? The object is at which position? Now look, the object is at 20 centimeters and 60 centimeters. But we can't have the 20 centimeters here. What I mean is that, look, here we have, these are 2 centimeters, these are 4, these are 6, these are 8, these are 12, 10, these are 12, these are 14, these are 16, these are 18. Now we don't have 20 here. So once we don't have the 20 there, what does it mean? We need a scale. Now, a scale must be that value which can divide this and gives us a lesser value. So I'm thinking of, when you divide these values here by 5, or even 10 would work, but that would be very small. So I want to use 5. So if I want to consider a scale of 5, that should be a number which can reduce. So 20 divided by 5 give us a 4 centimeters. A 60 divided by 5 give us a 12 centimeters. Hope you can now see that. And now if it gives us a 12 centimeters, what does it mean? It means that it means that 12 centimeters means that we can now count the 12 centimeters right on this, red diagram of ours. Now what we're going to do is, we need to get this first of all. And how are we going to get there? Like say for example, let's start off with say, now we are saying that now in our scale, let 1 centimeter represent 5 centimeters. That's what we have. Now what you must know is that I'll make an edit here, though I didn't put it in the calculation, but an edit would be that when you divide the 20 by 5, you divide this 20 by 5, here we shall get a 4 centimeters. When you divide this by 5, here you will get a 12 centimeters. Now, that's what you're going to be using. Now, what happens here is that we are going to, now, look, we have 4 centimeters as the object distance, meaning from the lens up to where the object is must be 4 centimeters. So let's count from here. We have from here up to here. So from here up to here is, now look, from here up to here is 1 centimeter, this is 2, this is 3, this is 4. So that the object must be around here, like that. Now place my object right there. Okay, great. This is how we're going to go about it. Now we have our object there. Allow me call it O. Now having done that, but object is height what? 2 centimeters. Now 2 centimeters, let's see, is that 2 centimeters? Have 1 right there and a 2 right there. So indeed it is 2 centimeters. Now what about the image distance? Is 12 centimeters. Now 12 centimeters at the other opposite side of the lens. So 12 from here, let's count. This will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You see 12 will be around here. Now once you have a 12 right there, it means that, okay, so now that's what we have. It means that, so it means that our image is going to be right here. But how long is the image? Image is 6 centimeters long, so it will be this. We have that 1 centimeter, 2, 3, 4, 5, 6. In fact, it's meant to be 6, so I think we went somewhere here. So now this is our image. Now why am I putting the image upside down? It's because you all know that the images formed by a convex mirror are always inverted. So that's why I'm doing it like that. Okay, now that's what we have as our image. Allow me call it just I, like that. Allow me call it I. Now after locating the images like that, you must now come back and know how does the rays move to form an image. How do rays move to form an image? How do rays move to form an image? Once you have them in place like that, because I've already given them to us, you must know now how the rays move to form an image. There's always a ray from the object there, incident onto the lens, right there. After that, this ray must always move from the pole of the lens there down to the, I assume that is a straight line, to the via that, coming down like that. Now that is it. But there's also a ray from the top of the object passing over the optical center and through the head of the image. So it will come like this. Okay, pass via that, the optical center C. It will come. Okay, like that. Or even if we just leave that aside, you can leave that aside. Can we leave this aside? Like now, we all know that in a convex lens, where this ray from the object cuts the principal axis, that point is always the focal length F. I don't know that that makes some bit of sense. That point is always the focal length F. And I think let's see, step in for that quickly without wasting time. Okay, I'll be erasing off this so that we put the real work and compare. Then we see the way forward. How we can determine the focal length using graphical method. Okay, so this has been just a rough cut. Let's now get into the real work, trying to rub off using my rubber. Okay, now after that, what are you going to do? So first of all, let's get the object. The object will be at this level. Why this level, by the way? Why this level? Is because it must be what distance? The distance must be 4 centimeters. Where the 4 centimeters? Count from here. 1, in fact, we have 1, 2, 3, 4. If you can count, there are 4 small squares here. 1, 2, 3, 4. You see that? That's why I have the 4 right here, as per the scale we have used. Then, having done that, we can now proceed. Now we need to put the image position also. The image position will be right there, and it is always inverted because you all know properties of images formed by the convex mirror lens. Now, why are we using the height 2? Because for me, I said you can even use 1, but make sure that it must be rhyming with this magnification. If you use 1, then the image height will be 3. If you use 2, then image height will be 6. If you use anything, you multiply by 3 so that you get the other. So the image height, object height is 2, and the image height is going to be 6 centimeters long. So let's see. Do we have the 2? Yeah, we have 1. Alright, so when you try to really look into this, when you count here, you have, when you count, you realize that you have In fact, let me just get a lesser pen so that we can count together. When you count here, look, we have from here up to here is 1, 2, 3, 4, 5, 6, and that's why I have it as 6 here long. What about this one here? Is just 1, 2, like that. Now you begin by locating the image position and object position, like that. Why is the object here? Because the object distance was 20, which you divide by 5 from this scale here, you get a 4, and indeed it is from 1, 2, 3, 4. You have right there. Object image distance is 60 divided by 5, you get a 12. So let's count. We have a 1, a 2, a 3, a 4, a 5, a 6, a 7, 8, 9, 10, 11, 12. We have it right there. Okay. Now after that, I told you that we must now get a line which must, okay, a ray which is incident right there, it must come in, and one which goes via to the bottom part of the image, which now this part where it cuts the principal axis becomes the focal length or the focal point, okay, or the principal focus. Now let's get that drawn. So we shall have our ray which will be incident to the pole right there in that direction. Now again we are going to have a ray which must go down to the head right here, which will come up to this level, a straight line up to that level from here up to right there. So we're going to have it as that. Okay, I hope you can now see that. Now where it cuts the x-axis here, that becomes our F, like have that. The arrow must be in that direction, and that's our object O, that's our image I. Now that is our F, that blinking part is now our F, the focal point. Now we shall name it that is F, which is our focal point. Maybe there's some definitions which you may need. Down here, O is the image, D is the object, I is the image, and F is the focal point. Now if that's the focal point, we need the focal length. Focal length must be the distance from here up to where that F is. The distance from here up to where that F is. The distance from here up to where that F is, simply. Now what we're going to do here is that, okay, from here up to where that blinking part is, when you count very well, how many small squares will you get? We shall get 3 small squares. Of course this is it. Let me get a lesser pen. Of course this is it. Look, 1, 2, 3. So there are 3 small squares. Actually 3 centimeters right there. There are 3 centimeters. And if there are 3 centimeters, what does it mean? It means that we are going to multiply it with the scale, because if there it is 3 from there, but the scale here is 5, each centimeter is 5, so we shall have to multiply. Therefore, let's get that reading so it away. So at that level, you must know that, okay, good, we must know that, okay, focal length is equal to a 3 times 5. I had explained that earlier on. Focal length is equal to 3 times 5, which will give us a 15. I've explained why it is that. By the way, I've explained why it is a 3 times 5, which will give us 15 centimeters. Remember, from the beginning of the story, our aim is to get power of a lens, which power of a lens is equal to a 1 over F, and F is the focal length in meters. Now we have our focal length 15 centimeters right there. Okay, now once I have our focal length 15, let's now go this level here, and we get some parts answered. Now in this level, still again, from the graph, focal length is equal to 15 centimeters. You have all seen that. Okay, now from the question, you have the statement from the question that they needed to determine whether the power of the lens was still in the acceptable range of positive 5 diopter and a positive 6 diopter. Now that's what they wanted. Now we are underlining the word power of a lens. We are underlining the word power of a lens. We are fully underlining this word power of a lens. Therefore, we shall now say that in the next part, power of a lens equals to a 1 over the focal length, but that must be in meters. Our focal length must be in meters. Now we shall again remind you that focal length was 15 centimeters, but we need to convert it to meters, like that. So converting it to meters, what are we going to do? We simply divide by 100. So therefore, we shall say that focal length equals to, when you divide by 100, you shall get a 0.15 meters. This is our focal length. Remember, our aim is to get the power, and to get the power we need focal length. So again, we're going to proceed and say that by substituting the formula of power of a lens to be 1 over 0.15. When you try to divide, our answer of power of a lens will be, power of a lens will give us a positive 6.67 diopter. Okay, 6.67. But now when you compare with these ones here, look, is it between that? It is beyond. So this one is beyond the required range. So it is not good. It is not good reason. It is very, very strong. It can even end up damaging your eyes. So we can conclude and say, that since the power of the selected lens in what you have 6.67 is greater than the acceptable range, okay, then we shall say that it is not suitable because it is too strong. Yeah, it is too strong because it can end up, okay, spoiling or damaging your eyes. Slow but sure. Okay, done with that, and that's part A quickly or perfectly answered. Of course, let's now go to the next part. The next part B, they're saying, okay, part B, decide whether the laser light in figure 2 will be trapped and transmitted through the pipe to the other end. Explain your answer. Now, they want us to explain this answer here. Would the laser pipe transmit the light to the other side? That's the question I have. Let's go right there. Now, the whole story begins with this. We shall now also have to move on. Now, we had this statement right away in the question. We had that statement in the question. The laser light is only trapped and transmitted. That's the simple reminder we are giving you here. A simple reminder that the laser light is only trapped and transmitted through the pipe to the other end by total internal reflection. Yeah, you have to bear that in mind. Now this one is what you call an optical fiber, and that's how the rays move. You see how the rays are moving? Now that's what we mean by moving through without it being transmitted, whereby at every end it is reflected back, more like the inside parts of the pipe are acting like a plane mirror. That's what we call total internal reflection. Look how cool that is. The way now, they're asking us that will the light be able to move like that, the way you're showing there? And what you're showing there is a total internal reflection. Okay. That aside, now we must first of all know what do we know about total internal reflection. And that aside, if we try to refer back to, let's go here. If you try to refer back, look at this. Okay. Look at this. Now here, they've given us this. Then they're saying that refractive index of the glass material is 1.47. Hope you can now see that. Maybe, by the way, in the other question which you have done, there was this in here that height of the medical record is 2 centimeters. The other question here from doing the part A, height of the medical record is given as 2. Then the other one becomes 6. There's some guidance there given to you in that figure. We didn't pay much attention there, though in our guide still everything was fine. Now the refractive index is 1.47 of the glass material here. Now, is there use of that refractive index? Let's go and look into that. Is there use? We shall be seeing that. So let's go and see if there is use for that refractive index. Now, back to our question. What must you know is, what do we mean by this one here? Total internal reflection. Like, why is the inside part of the pipe acting like a plane mirror, which we see in simple terms we call total internal reflection? Like, why is it behaving like that? That's what you're asking here. Now, let's move on. All right. Now, still, before we go there, let's go and understand what total internal reflection means. Please, this is not in the guide, but I just want to bring it before we can come back to this and understand something. Let's go. Okay, good. Now, you realize that in this part, we have something for you. And we are here to remind you that, okay, we want to understand what total internal reflection means and which terminologies do we use there. First of all, in the statement format, we have this corner, a reminder corner, where we shall have to understand what total total internal reflection means, then we shall go back to the other question and we get it answered very well. Because they were asking, will the laser light be able to move without it being transmitted? Meaning, will it be totally internally reflected inside there? Now you must be knowing under which conditions do we always get what we call total internal reflections. Okay, very good. Now in that script which is coming over, we got you covered. Okay, without wasting time, this picture is here for you. Now let's understand total internal reflection under normal circumstances. Now we are looking at a situation where, assuming if light is coming from glass down this side, in this picture A, light is coming from glass down this side. Now light is coming from glass. Okay, so now what we have here, you realize that when light is coming from down this side, when light is coming from down this side, the light will come from there. Now this one, first of all, for total internal reflection it must be that light must be coming from a more optically dense medium compared to coming to a less optically dense medium. That's what you must know. And just like you're seeing, light is coming from glass, coming over this side. Now, due to change in the optical densities, the light will be refracted away from the normal, like you can see there. Now, what happens when, now here you must know that inside here we have what we call the angle of incidence. The angle of incidence at which this is taking place. Now that angle of incidence there, what if when that angle of incidence is increased? Like originally here, it is small. Now here we increase the angle of incidence. Like you're seeing, there is some big distance compared to the picture A. So increasing the angle of incidence, this ray also keeps on, the more we add on the angle of incidence, this ray also moves away from the normal. Like you can see here, it has moved away from the normal. I don't know if you can see that. Now again, if you go on increasing the angle of incidence like this, like they have done here, increasing the angle of incidence, this ray will start now to graze onto the glass air boundary like we have here. Now in this point, whereby, now what you must know is that in this context, you must know that here, I'll erase off this. Allow me to erase off this. Now this one here is the angle of refraction, and this one here is the angle of incidence I. You see that? Now that point when the angle of incidence, so long as if the angle of refraction, when the angle of refraction becomes 90 degrees, or it is going on the surface the way you're seeing it here, then the angle of incidence here, I, we no longer call it angle of incidence, but we call it critical angle. We call it critical angle. Now, critical angle is the angle of incidence when the angle of refraction is 90 degrees. We have it here that the critical angle is the incident angle at which the light traveling from a denser to a less dense medium results in an angle of refraction of 90 degrees. I don't know if I can see that. Okay, results in an angle of refraction of 90 degrees, like you can see. Once the angle of refraction becomes 90, the angle of incidence, we no longer call it angle of incidence, but we call it a critical angle. And once this critical angle is exceeded like this, once this critical angle is exceeded like this ray will no longer graze on the surface, but will come inside like that. And that's what we have in this picture here, which we call total internal reflection, whereby the ray has stopped grazing, but it automatically comes inside. It is reflected back inside the more optically dense medium. So when does total internal reflection occur? Total internal reflection occurs if the angle of incidence is beyond the critical angle. Once angle of incidence is beyond the critical angle, then total internal reflection takes place. Of course, you have that total internal reflection is the phenomenon that occurs when the angle of incidence exceeds the critical angle. Now, for you to take this, when the angle of incidence is beyond the critical angle, then total internal reflection takes place. And this is what we are going to look at in the other question. So, our new term is critical angle. So, we need to find the critical angle versus the picture we have. If the angle of incidence is greater than critical angle, then total internal reflection can take place. Hope that explanation brings some bit of sense. Anyway, now back to this. Again, we shall remind you that now we shall need to do what? Determining the critical angle C of the pipe, glass pipe. Now I think we need the critical angle, the same of critical angle is C. We need to determine the critical angle. And look, if we find that this 45, which is our angle of incidence here, is 45, 5. Once you find that this 45 is greater than the value of C you're going to find, then total internal reflection will take place, which total internal reflection allows the light rays to move like this without being transmitted. Let's look into that. Now, from the formula we know that N is equal to that, whereby N is the refractive index of glass and C is the critical angle. But we know that the refractive index was 1.47, so we substitute in the formula, we shall get, when we substitute in the formula, we shall come up with that. Now what do we mean? Our N is this right there. Now we need to get the value of C, so we shall now say that sin C is equal to a 1 over 1.47. Now we need the value of C, so we shall need to get the inverse, so sin C is equal to, when you divide this, you come up with that. Alright, great. So C will now be equal to sine inverse of that, and therefore our value of C will be a 42.8 degrees. Now let's compare. We said that if the angle of incidence is greater than the critical angle, okay, so now we say that once the angle of incidence is greater than critical angle, then total internal reflection occurs, of which total internal reflection is what we have just right there. Now look at this. Look at this. The angle of incidence is 45, which is greater than the 42.8. Remember, this one was the angle of incidence, which I have right here at the beginning. Now, of which this is our critical angle, and it is greater, so therefore total internal reflection will take place. So let's conclude and say, you cannot conclude and say, okay, we say that since the angle of incidence of glass is greater than the critical angle, yes, total internal reflection will occur and the laser light will be trapped and transmitted to the other end of the pipe. I hope you can now really see that coming or reasoning out in simple terms. So we have successfully answered part B. Let's now go and look at part C in simple terms. So part C, they're now telling us that explain why laser light is preferred over ordinary light. Let's go to that very fast. Why is laser light preferred to? Okay, let's go there. Part C. Why do we prefer laser light compared to the other? Now the reasons are just right here. The reasons are just right here. We said that laser light is preferred over ordinary light for medical endoscopic procedure because it is, now one, it consists of one wavelength giving a high clarity in imaging. Yeah, it has one wavelength which gives a high clarity in imaging. Next, now some of these are self-explanatory, I may not bother to explain all that. So waves are in phase, producing a stable and precise patterns. So in phase we mean like this, it must be like this, that's in phase. Now the one out of phase means this. Out of phase means this one is big, this one is small, like that, like that, like that is out of phase. This is in phase. Okay, provides bright and highly concentrated illumination for detailed work. Then also has a high penetrating power. I've said I'm not going to that deep. You can at least look at that also. Or we can also say that can travel long distances without spreading out much. Okay, that's how we use laser light other than the local light which we use in everyday life in simple terms. Let's now proceed still. Now proceeding. Okay, here we are. They're saying explain how understanding pitch, loudness, and quality or timbre helps distinguish between different musical notes. Now you must know what timbre means, what pitch means in simple terms. What pitch means in simple terms. Alright, good. Okay, let's get the part D of the question answered quickly. Let's get part D of the question answered quickly. So now shall again remind you that pitch, first of all, you need to know what pitch is. We need to know what pitch is, so we shall now tell you that. Okay, great. Pitch is the loudness or lowness of sound, and it depends on, so pitch is the loudness or lowness of sound, and depends on what? Now pitch depends on frequency. which means that frequency produced of the frequency produced, meaning that the higher the frequency, the higher the pitch, and vice versa. So vice versa means the lower the frequency, then the lower the pitch. Now that's about that. Another fact about pitch is what we call timbre. Now timbre, this depends on the type of instrument being played and how it produces vibration. Now timbre means, like say for example, we have the stringed instruments, like say this. I have this stringed instrument here. You have all ever seen an instrument which is like this, like with the strings there, a harp, then also a drum. So the timbre of a drum is different from that of a harp. This is a stringed instrument. This one here is okay, made out of skin actually. So timbre, it depends on the type of instrument being played and how it produces vibration. Yes, vibration on the stringed instrument is different from that of a drum. Okay, two instruments, a drum and a piano, can play a sound of the same frequency and the same amplitude, yet their quality differs. Yes, when they play a drum and then they play, or maybe for example, we have the solo first, the do, re, mi, fa, so, la, ti, do. Like if we sound a mi on a drum and on a piano, they'll be totally different. That's what I mean by timbre. Okay, this difference in timbre is what allows us to easily distinguish the sound of one instrument from another when they play the same note at the same volume. So that's what makes the difference. But let's try to explain that. The timbre, the pitch. Pitch means how high or how low. Now the timbre depends on to the type of instrument we are being sounded at that moment. Okay, I didn't bother with this last point because I know it's just self-explanatory. I may not bother with that a lot. Thank you for watching. Don't forget to subscribe.